Welcome to our exploration of inner product spaces, where we'll delve into the concepts of orthogonality and norms, essential components in understanding vector spaces. The motivation for defining an inner product in a vector space comes from the desire to generalize familiar geometric ideas like length, distance and angle from Euclidean geometry, R2, R3, to more abstract vector spaces, like spaces of functions, polynomials or higher dimensional spaces. An inner product space is a vector space V over the field real numbers or complex numbers together with a function, called an inner product, from V cross V to F that satisfies the following axioms for all U, V, W belongs to V and scalar A belongs to F. The first axiom is positivity. It says the inner product of two equal vectors should always be greater than or equal to 0. And it is 0 only if the vector itself is the 0 vector. 2. Conjugate symmetry says the inner product of U, V equals to conjugate of the inner product of V, U. The third axiom is linearity in the first argument, that is, the inner product of two vectors O plus W with V is equal to A times the inner product of U and V plus the inner product of W and V. In the vector space R(n), the standard inner product, also called dot product, is defined by summing the products of corresponding components. This operation satisfies positivity, as sum of the squares of real numbers is always greater than 0 and it is equal to 0 only if each component is 0 and hence U is 0. Conjugate symmetry holds, due to the commutative property of real numbers, linearity can be easily established. Please check out the calculation. Similarly, in the complex vector space Cn, the standard inner product involves the sum of products of components, incorporating complex conjugates. Note that z multiplied by z bar gives modulus of z square. Conjugate of z is equal to z and conjugate of z1 plus z2 is equal to conjugate of z1 plus conjugate of z2. Using this we can easily establish axioms of positivity, conjugate symmetry, and linearity. Let V be an inner product space. If U belongs to V, then the norm or length of the vector U is defined as the positive square root of the inner product of U with U. Further note that if x and y belong to V, then the norm of x minus y denotes the distance between the vectors x and y. Further, if U belong to R3 then norm of U is equal to the square root of U1 square plus U2 square plus U3 square. A vector is called unit vector if its norm is 1. Further, the vector U is called orthogonal to V if the inner product of U and V is equal to 0. It can easily be checked using conjugate symmetry that if U is orthogonal to V then V is orthogonal to U. Likewise, if U is orthogonal to V then any scalar multiple of U is also orthogonal to versus and 0 is the only vector orthogonal to itself. Here we give some definitions. Orthogonal sets consist of mutually perpendicular vectors. Further, orthonormal sets are orthogonal sets in which all vectors has unit norm. The triangle inequality holds in inner product spaces, that is, if x and y represent sides of two vectors, then the sum of the two sides is always greater than or equal to the third side. Schwarz's inequality, the absolute value of the inner product, a kind of generalized dot product, of two vectors is always less than or equal to the product of their norms, lengths. Pythagoras theorem. It says that if x and y are orthogonal vectors, then the sum of the squares of the two sides is always equal to the square of the third side. Let's apply these concepts to solve problems, such as computing norms and verifying inequalities, to solidify our understanding of inner product spaces in practical scenarios. By verifying the Pythagoras theorem and checking orthonormality in R2, we reinforce our grasp of these mathematical principles, demonstrating their consistency and utility in various dimensions.